All right, finishing up Unit 7 here. We're on topic 7.8, and we're going to deal with exponential models with differential equations today. And we will show how models of exponential growth and decay are derived from this differential equation, dy dx equals ky. Remember when we did direct and inverse variation? That's all we're dealing with here. This is a direct variation problem. So, what to look for? The rate of change of a quantity is proportional to that quantity itself. If we see something in a word problem like that the rate of change, that's my dy dx, is proportional to that quantity itself, then that's direct variation. That's like directly proportional. Now, what I want to show you, though, is that we can separate these variables, all right? So I have dy equals ky dx, which means I need to divide both sides by y. So I have 1 over y dy equals k dx. All right? Remember that k is just a constant, just a number. All right, so if I integrate both sides now, I'm now going to have the natural log of the absolute value of y equals kx plus c. All right? And we're used to this. If I exponentiate both sides, okay, we have done this before. Exponentiate both sides. That helps me get my y by itself. So now I've got the absolute value of y equal to, now before we move on, remember that this can be e to the kx times e to the c. All right? And we just call this thing c. All right? So we now have that this is equal to c e to the kx, all right, and y equals, it could be plus or minus c e to the kx. I want you to notice this little note down in the corner. The sign is determined by the initial condition. We've dealt with that before as well. All right, we have to consider the initial condition. All right. So let's look at a couple examples to see how we're going to use this exponential model idea. Now this one doesn't mention a whole lot about something growing or whatever exponentially, but it does have this situation dy dx equals 2y, all right? And so if you remember what we just came up with, y equals c e to the kx. We just came up with that. All right, and where did we get it? We got it from dy dx equals ky. All right, if you ever forget this piece here, if you remember this piece, you can always do the work and get back over to here. All right, now what I want you to see on this problem is that this number 2 is my k. All right, dy dx equals 2y. That is the k. So what I can do now is I can plug in all of these values that I've got. I've got this k value, I've got y is 1, I've got x is 0, and I can plug those in over here. All right, so my y value is 1. That equals c e to the 2 times 0. Just plugging in all those values over here. Well, this is going to be e to the 0, which is 1. So I just have that c equals 1. All right. And that means that we're still not done. Okay? We just have enough information to move forward because it's asking what is the value of x when y equals 3? Well, what we have now is we have, if we use our y equals c e to the kx, I now know what c is. So I have y equals e to the 2x, because my c value, remember, is 1. We just found that out. All right, so now we have y equals e to the 2x, and now we can work with this question. What's x? What's x when y equals 3? All right, that's the question we're looking for. So now I can put the 3 in. So 3 equals e to the 2x, and algebraically, knowing what we know about logarithms, we should be able to do this. Take the natural log of both sides, because we know that taking the natural log of e to the mess is the mess. So that's 2x equals the natural log of 3. So my x value is the natural log of 3, all divided by 2. All right? Now, the next problem. Population y grows according to the equation. All right, now they've told us that equation that we're familiar with. And we know, though, that we're going to use this. Y equals c e to the k, and I'll just use t instead of x since they did. All right? K is a constant, and t is measured in years. If the population doubles every 10 years, then the value of k is, all right? So our population is doubling, so I can put a 2 in here for y. Okay? And so this value here needs to be twice the c value. All right? And that happens every 10 years. And from that point on, it's just like the last problem. All right? So now I have 2 equal to e to the 10k, and it's literally the same process as the last problem. We're going to take the natural log of both sides, all right, which is going to leave me with the natural log of 2 equals 10k. So k equals the natural log of 2 divided by 10, and that decimal is 0.069. Remember, in calculus, decimal answers are to 3 places. All right, let's keep moving here. If dy dx equals 4y, once again, this is my k. All right, don't forget that. So it's really pretty easy if you just remember this. Y equals c e to the kx. That's a formula that we're going to have to kind of commit to memory, but I showed you how we came up with the formula. So my y value is 4. Looking for c. My k value is also going to be 4 when we get there. Okay, but I have k times 0 right now. All right, and so that's e to the 0. E to the 0 is 1. My c value is 4. And my equation now is y equals 4e to the 4x. Notice it's kind of odd, this problem. The c value and the k value wound up being the same thing, but don't separate we need to keep those separate, I guess is what I'm trying to say. Be careful with how you plug those in. Okay? Let's see if we can squeeze anything else in here. What do we take away? Look for this key phrase, rate of change is proportional to the amount. All right? And then our general solution is always this. All right? And we will stop there for today.